Ever wonder how Dropbox stores your files? Is it really magic file dust? Let's dive into distributed file storage architecture, the secrets behind the cloud.
Let's explore designing a distributed file storage system like Dropbox or Google Drive. We'll cover core components, data consistency, scaling, and fault-tolerant strategies in detail. Imagine building a system to store billions of files. Key components include storage servers, metadata management, and synchronization services. Let's dive into each of these. The storage layer handles actual file storage using object storage like Amazon S3 or Google Cloud Storage. These provide scalability and durability. This layer stores the raw data. Metadata management stores file names, permissions, and locations. A database like Cassandra or DynamoDB handles this, offering fast lookups and high availability. Think of it as the index. Let's dive into the right path, how a file gets uploaded and stored. First, the client uploads the file. This upload hits a load balancer, which distributes the traffic to a cluster of write servers. These servers pre-process the data. The write server then streams the file data to a message queue, such as Kafka. Kafka partitions the stream for parallel processing. From Kafka, the data flows into the storage layer. Here we can use object storage like S3 or a distributed file system. For handling large uploads, asynchronous processing is essential, preventing the user interface from freezing. This is where message queues become incredibly useful. Imagine a user uploading a large video. Instead of directly processing it, we enqueue a message with the file's location and processing instructions. Services like RabbitMQ or Kafka then distribute the processing load across multiple workers. This ensures a responsive experience even with heavy background tasks. To further optimize performance, consider implementing a caching layer. Caching frequently accessed files or metadata reduces latency and server load significantly. Asynchronous processing is vital. We use message queues like Kafka to handle file uploads, ensuring reliability and preventing overload. Kafka enables decoupled architecture. Upload requests are placed in the queue, then processed independently. This prevents blocking the main application. Caching is crucial for frequently accessed files. A CDN like Cloudflare can cache files closer to users, reducing latency. Caching strategies are key. We use a combination of CDN caching, in-memory caching, Redis, and database caching to optimize performance. To manage file access and ensure security, we can implement an Envoy proxy as a gateway. Envoy handles authentication, authorization, and traffic routing efficiently, adding a crucial security layer. Envoy's advanced features like rate limiting and circuit breaking help protect our storage system from overload and cascading failures. These are essential for maintaining stability and responsiveness. For monitoring and observability, Prometheus can track key metrics like file access latency, storage usage, and error rates. This provides insights into system health and performance over time. Alert Manager, integrated with Prometheus, notifies us of any anomalies or critical issues, ensuring timely intervention and minimizing downtime. This proactive approach is key for maintaining a reliable system. To manage the traffic efficiently, we can introduce Envoy as a reverse proxy, routing requests to different storage clusters. Envoy also offers robust load balancing and health checks, ensuring optimal resource utilization. To monitor the health and performance of our distributed file storage, we can use Prometheus to gather metrics. We track request latency, storage utilization, and error rates, visualizing them with Grafana dashboards. To improve the system's resilience, we can implement circuit breakers. If a storage cluster becomes unavailable, the circuit breaker trips, preventing further requests from reaching it and causing cascading failures. The circuit breaker monitors the failing cluster's recovery, and once the cluster becomes available again, the circuit breaker closes, allowing traffic to flow through it. This maintains a stable system. To scale effectively, sharding files across multiple storage nodes becomes essential. Consistent hashing ensures even data distribution and minimizes data movement during scaling events. This reduces hotspots. Implementing replication, such as triple replication, enhances fault tolerance. Data is stored on 3 different nodes, guaranteeing availability even if 1 or 2 nodes fail. This impacts costs. Monitoring the system involves tracking key metrics like storage utilization, read/write latency, and error rates. Prometheus is useful for collecting metrics, and Grafana for visualizing them effectively. In summary, designing a distributed file storage system requires careful consideration of data consistency, fault tolerance, scaling, and security.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.